So we talked about precipitation reactions, and we predicted the products by just swapping the ions. And there are two other types of reactions that can occur when you have solutions combining and ions changing places. Those are the acid-base and gas evolution reactions. Acid-base reactions are also called neutralization reactions. They involve the reaction between an acid and a base, in which the acid and the base neutralize each other. When this happens, we get water forming and an electrolyte generally. Yeah, there's something wrong with that slide. Anyway, a gas evolution reaction produces a gas. A gas is evolved. We usually see this as bubbling or fizzing. So we're going to look at the acid-base reactions first. In Chem 1B, you'll study a lot more about acids. We're just going to use the Arrhenius definition of acids, which is the one that we used when we were talking about how to name them. An acid is a substance that can produce hydrogen ions in aqueous solution. So HCl, aqueous, we learned to name that as an acid. What would the name of this acid be? Hydrochloric acid. When you put that in water, it ionizes or dissociates into hydrogen ions and chloride ions. It's a molecular compound, but in water it becomes an ion. The hydrogen from the acid molecule gets donated to a water molecule, and that forms what's called the hydronium ion. So this H+, let's think about H+. A hydrogen atom has how many protons and electrons? One. It has one proton, one electron. When it becomes an H+ ion, it loses its only electron. So all that's left is a proton. A hydrogen ion is a bare, naked proton. And that proton is not very happy all by itself. It's not going to be very stable. And so what's going to happen is it's going to attach itself to something else. In an aqueous solution, what there's a lot of is water molecules. And so that extra hydrogen will attach itself to the water molecule. And because it's missing an electron, now this new substance here has a positive charge. So it's got H3O+, and the name is hydronium ion. So in my chemistry land, I think of the hydrogen ion as being a little bit like a newborn baby, too small to go out by himself. So you do not see newborn babies just strolling down the sidewalk by themselves, right? There's always someone with them. And so hydrogen ions are actually never out by themselves. They're always with someone. So here the hydrogen ion was with chloride in this molecule. When these separate, the hydrogen can't stand being by itself, and so it's going to ride piggyback on a water molecule. So chemists often use H+ and H3O+ interchangeably, because just talking about H+ makes all the equations much simpler, but that doesn't actually reflect what's going on in the solution. The hydrogen ions are not going around all by themselves. They're actually on a water molecule. So hopefully that won't be too confusing. So those are acids. Bases are substances that produce hydroxide ion in aqueous solution. Most of the bases we'll encounter are going to be metal hydroxides, like sodium hydroxide, an ionic compound of a metal and hydroxide ion. When you put this in water, it's soluble and it separates into sodium ions and hydroxide ions. It produces hydroxide ions. It's a base. There are other substances such as ammonia, NH3, that act as bases, but they do not contain hydroxide ions. And what happens with the ammonia is it actually pulls a hydrogen ion off of the water. Let me just write that in here real quick. NH3 plus H2O. Well, technically it's this. It can steal a hydrogen ion from the water and make the water into hydroxide ion. So that's how ammonia becomes a base. But for the most part right now, we're just going to be looking at metal hydroxides. Some acids have more than one hydrogen that can come off. And so those are called polyprotic acids. Poly meaning many, protic referring to protons. So that ionizable hydrogen is a proton. It's a hydrogen ion. So polyprotic, they have more than one ionizable proton, and they release them sequentially, one at a time. One comes off, and then the next one, and then the third one if there is one. So sulfuric acid is an example of a diprotic acid. We can see from the formula H2SO4. In acid formulas, the hydrogen ion that's ionizable is written first. That's why when we write acetic acid, we write HC2H3O2. These three hydrogens do not ionize. And so those are included over here as part of the acetate ion. This hydrogen at the beginning is the one that forms the ion and comes off.
Which acid is that?
This is acetic acid. So here, H2SO4, there are two hydrogens, and so this is called a diprotic acid. There are also triprotic acids like phosphoric acid, H3PO4. So what happens is you get the H2SO4, and when you put this in water, it will ionize. The hydrogen ion that's formed goes and rides piggyback on the water molecule, making a hydronium ion, and then you have hydrogen sulfate ion that's left. So one hydrogen comes off. This ion also has an ionizable hydrogen, and so if we add another water to that, yeah, this is why. Okay. Oh, I didn't mean to do that. Let me back this up.
Is it always just one? It always gives or takes one hydrogen?
They come off one at a time.
Okay.
So let's just do it this way. This is one of the reasons that we often pretend that hydronium doesn't exist. So here I'm going to draw this as just a bare proton, even though we know it's going to ride piggyback. And then that hydrogen sulfate ion can also come apart and give a hydrogen ion. So overall, this can lose two hydrogen ions. It does so, though, one at a time. We also have bases that can produce more than one mole of hydroxide ion. If you have something like calcium hydroxide, and you put that in water and it ionizes, you're going to get one calcium ion and two hydroxide ions. There's no special name for bases like that, though. Any questions? Yes?
So the peroxides can come off two at a time? Like it won't go sequential like the H plus would?
That's a very good question. So the hydroxides, these are soluble ionic compounds, and they're going to ionize completely. So acids, we talked about strong acids and weak acids. Sulfuric acid is actually a strong acid in the first ionizable proton, so it will go completely to hydrogen ion and hydrogen sulfate. But this second one is considered a weak acid, and so only a little bit of the second one ionizes. And that is the case, well actually, sulfuric acid is the only strong multiprotic or polyprotic acid. Phosphoric acid is a triprotic acid, but it's weak in all three of its protons. So one will come off and you'll have dihydrogen phosphate, and then that will ionize a little bit, and then hydrogen phosphate will ionize a little bit. And that all gets kind of complicated, as you might imagine. And that's a subject for Chem 1B. But the reason that the bases do not do that, they do both come off at the same time because they either dissolve or they don't dissolve. They don't partially dissolve. Okay, any other questions? Okay, so in an acid-base reaction, we've got the acid producing hydrogen ions, and we've got the base producing hydroxide ions. The hydrogen from the acid combines with the hydroxide from the base, and those combine to make water. So here we have an acid, hydrochloric acid, and we have sodium hydroxide as the base. These are going to do that same double exchange, switching of partners, and they're going to form water and salt. And by the word salt, chemists mean an ionic compound. It could be sodium chloride, it could be potassium iodide, it could be ammonium nitrate. Any ionic compound is a salt. Table salt is sodium chloride. So we've got water forming and we've got salt forming. So let me show you what that looks like. So let's get rid of these labels. And let's look at this in terms of it being a double replacement reaction in the sense that the precipitation reactions were. So what we did is we looked at the ions that are formed from the first compound and the ions that are formed from the second compound. And then we said, okay, well, they went to this party and they're going to mix and mingle, and we're going to see if they hit it off with anybody. So we're going to try sodium and chloride together, and we're going to try hydrogen ion and hydroxide ion together. So here's hydrogen ion and hydroxide ion, and here's sodium ion and chloride ion. So we put sodium and chloride together, +1, -1, they would make sodium chloride. We know that's aqueous from general knowledge and also from the solubility rules. H plus and OH minus. If you just stick those two ions together, you get HO. HOH, and you look at that and you're like, that's kind of funny looking. Oh, that's H2O, right? So hydrogen ion and hydroxide ion make H2O. H2O is a molecular compound and it's a liquid. So that's where we get the water and the salt. Any questions? If we do the net ionic equation for this, this is a strong acid, and this is a soluble compound. This is a soluble compound, so we would split that into ions. This is a liquid. This would not get split into ions. So when we cross out the spectators, this is the net ionic equation that we end up with. And this is going to be the net ionic equation for most acid-base reactions. Yes?
And when you say the net ionic equation, that's literally splitting each part up, correct?
Yeah.
Okay.
Yeah. So if we look at these separately, because they're separated in the solution, this one is not. So let's, these are separated. We've got sodium on the one side, and we've got sodium on the other side, and we've got chloride on this side, and we've got chloride on that side. And so what we've got left is hydrogen ion plus hydroxide ion making the water. So the sodium ion and the chloride ion didn't actually participate in any chemical reaction. They were just spectators. They were there. So here's illustration of what's going on. Here we have hydrochloric acid dissolved in water. So here are the chloride ions that form. the hydrogen ions are riding piggyback on the water molecules. And here we have sodium hydroxide, there's sodium ions, and there's hydroxide ions. And when these mix together, the hydronium ion gives one of its hydrogen ions to the hydroxide. So we've got the H3O plus getting together with the OH minus. This one is thinking, I've got an extra hydrogen ion. Not super crazy about this. I'm dealing with it, but I'm not real happy about it. And this is a water molecule saying, hey, I lost a hydrogen ion. I'd like another one. Anybody have an extra? And this one's saying, hey, I have an extra one. How about I give you this extra hydrogen ion, and then we can both go back to being water molecules. And so that's what happens, and you end up with two water molecules. So the hydrogen ion is riding piggyback on a water molecule, but it can just like be bounced around, given to other things. I think of it as this maybe being the parent who had given the baby to a babysitter to hold, and now the babysitter's just going to give it back. So we'll see that hydrogen ions can just kind of go back and forth. They get passed off a lot like a little kid at a party. And what we have down here, all the hydronium ions and the hydroxide ions got together and switched back and forth until they made water molecules, and all we've got left in solution now is sodium and chloride ions. So we've got salty water. Any questions? Here's some common acids and bases. So these are the strong acids. There's the list that we were missing earlier. Hydrochloric, hydrobromic, hydroiodic, nitric, sulfuric, and perchloric. Those are all strong acids, meaning when they are in solution, aqueous solution, they ionize completely. Acetic acid is a weak acid. That's the acid in vinegar. Hydrofluoric acid is also a weak acid. And here we have some common bases: sodium, lithium, and potassium hydroxide. Those guys are very soluble. Calcium hydroxide and barium hydroxide are somewhat soluble. They're not as soluble. And then we have ammonia. Ammonia is a weak base. The rest of these are strong bases. Yes?
So when those acids are put into a solution, they break apart, correct? And then the bases collect everything.
Yes.
Okay.
Yep. And this is the equation by which ammonia produces hydroxide ion in solution. It does so by taking a hydrogen ion from the water to form ammonium ion, and then what's left is hydroxide ion. So let's write a molecular and a net ionic equation for this. Yes?
So if you, let's say you accidentally spill an acid on your hand, you have a base right there, should you pour some of the base in water and then put your hand in that?
That's a good question. So you spill acid on your hand. Should you dip your hand in base then to neutralize it? I think it's probably the safest thing is to just wash it off with water. Yeah. The thing is, bases are also damaging to your skin. And if you don't have just the right amounts, you could actually end up making things worse. Yeah. But that's a good question. In terms of neutralizing acids or bases, the weak acids and bases are safer to use because they don't ionize as much. And so baking soda makes a really good neutralizer because it can actually act as an acid or a base and can neutralize both. It's better at neutralizing acids, but it can neutralize bases. So baking soda is a good thing to put on stuff.
Like I was just thinking because of the citric acid that you were using back there, like when you were using the NaOH, how I just showed that was a strong base. You're going to neutralize with it. So I had some citric acid on hand and I had a bunch of sodium hydroxide.
Yeah. The thing is, when you're just mixing them, you can't tell what you've got more of. And so on Tuesday, when I was pouring solutions and making them pink and clear, the phenolphthalein indicator tells me, okay, this is very basic. this is very acidic, and when it's just that pale pink color, I know I'm right in the middle and have it pretty well neutralized. But without the indicator, it's hard to tell. Those are good questions. So let's write equations. Reaction between sulfuric acid, oh, there's a typo. That's supposed to be a subscript, and aqueous lithium hydroxide. Now it's a subscript. So aqueous H2SO4. So that's one of the reactants, H2SO4, aqueous, and aqueous lithium hydroxide. I really need to stop playing with my iPad while I eat popcorn. It gets the screen very greasy and it doesn't work so well. Okay, so what are we going to end up with? What do we do? We're going to treat this the same way we did precipitation reactions. Look at the individual ions, swap the partners, combine them in the new way, and see what we end up with. So H2SO4. Well, in neutralization reactions, all the hydrogen ions are going to react. And so we're going to pull both of them off. So we'll divide this into sulfate and hydrogen ion. So we'll get H plus and SO4, 2 minus. And then this aqueous compound over here, lithium plus and OH minus. So we're going to try lithium with sulfate and hydrogen with hydroxide. The order in which you write them doesn't matter in terms of whether you do hydrogen and hydroxide first or last, but you always have to write the positive ion first. So we've got H plus and OH minus, and then we've got lithium plus and SO4, 2 minus. So we're going to combine these together. H plus and OH minus, plus 1, minus 1, we just push them together, but that makes H2O. Water. And it doesn't tell us what the state, or it doesn't tell us what the temperature is. If there's no temperature specified, you can assume room temperature. So at room temperature, we should know that water is a liquid. And so the state symbol for this would be L. And then we've got this lithium with a plus 1 and sulfate with minus 2. We're going to need 2 lithiums to balance the charge on the sulfate. So the formula is going to be Li2SO4. And then we have to ask ourselves, is that a soluble ionic compound?
Lithium.
Yeah. Sodium, lithium, potassium, and ammonium salts are soluble, no exceptions. So we're going to put AQ for the state symbol on that one. So there's a molecular equation. Is it balanced? No. This is a diprotic acid. And so the diprotic acid is going to need 2 moles of the hydroxide. So we're going to need 2 of those. So doing that, I've got 2 lithiums and 2 lithiums. I've got 1 sulfate and 1 sulfate. Here I've got 2 hydrogens and 2 more here, that's 4. So I need to put 2 molecules of water. And then I've got 2 oxygens from here, and that's going to make the 2 oxygens there. You can do the sulfur and the oxygen separately as well if you wish. But that's our molecular equation.
Doesn't that
So what's the net ionic equation? We're going to get H plus OH minus to make H2O.
And that's after you took out all the
That's after taking out the spectators. So let's look at the spectators. So this is an acid. Yeah, question?
Yeah, can you just explain again, like, why you took off one H when, like, H2SO4, there's two H's? That's, you said, you don't understand.
Oh, why there's only H plus here? Well, if we were making this into an equation, there would be 2 hydrogen ions. But usually when we're looking at how to combine things, we're not concerned with the numbers. Like over here, I wrote 1 lithium and 1 sulfate, and then I'm putting together based on the charges. Here, when I'm taking this apart, I know that it's a hydrogen ion, it's not an H2, 2 plus ion. But let's go ahead and look at the complete ionic equation and how those spectators would go away. So this would be 2 hydrogen ions and sulfate, and then this would be 2 lithiums and 2 hydroxides. It's kind of cramped up in here. There, how's that? Marginal. Yeah, let's just start over. It's not working out. So we got 2 hydrogen ions, and we had a sulfate ion. It's a minus. And we've got 2 lithium ions, and we've got 2 hydroxide ions. And then over here, do we break the water into ions? No, because it's a liquid. If it's got liquid, solid, or gas as its state, we need to just leave it alone. H2O. And then we're going to have 2 lithiums and a sulfate. So that's my quick sketch of the total ionic equation. We've got 2 lithiums on each side, we've got 1 sulfate on each side, and so we cancel those out. And then what we've got left is 2 hydrogen ions, 2 hydroxide ions, and 2 water molecules. And then we just divide all the coefficients by 2, and we get this for our net ionic equation. Any questions? Yes?
Do we have to put the states when we ask for it then?
You should put the states. If the question specifically mentions the states, then you absolutely have to. If it doesn't mention it, then no, you wouldn't necessarily have to write them. But I think when you're writing these sorts of equations, it's a good idea.
You have to on mastering chemistry too.
Yeah, mastering chemistry really wants you to put the states in. And I understand that writing equations in mastering chemistry is very tedious, and it's very, very picky. But you do get that immediate feedback of seeing what's right. And I think what happens to students sometimes when they just, do work by hand and then they check it against the answer in the back of the book, sometimes you don't notice the little error that you made, that you've got the 2 on the wrong side of the parenthesis or something. Mastering chemistry notices those things. And so as annoying as it can be, I think it is a good thing. Acid-base titrations. We did these on Tuesday. So in a titration, we have a substance in a solution of known concentration, and we react it with another substance in a solution of unknown concentration. So what we did is we made a solution of oxalic acid. We weighed out the oxalic acid, so we know what that is. Then we reacted it with sodium hydroxide in the burette. And based on that reaction, then we calculate the molarity of the sodium hydroxide. It's a very common laboratory technique. So we're going to add the one solution to the other until the reactants are in their stoichiometric ratio. There's not going to be an excess reactant. We're trying to get them just right. That's called the equivalence point. and then we can calculate the unknown concentration using stoichiometry. We can't see what's happening when we reach the equivalence point, and so we use the indicator. The indicator is usually an organic dye that changes color in response to changes in acidity or alkalinity in terms of hydrogen ions and hydroxide ion concentrations. It will change color. And so we used phenolphthalein, and it was colorless in acid solution, and then it turned bright pink in very basic solution. And so when we got to that place in the middle, that sweet spot of that just very pale pink, then we knew we were very close to the equivalence point. At the equivalence point, in an acid-base titration, the number of moles of hydrogen ion equals the number of moles of hydroxide ion. And so we can calculate. Yes?
If, like, say scientists didn't have an indicator, then how would they, like, chemically figure it out?
There are ways to do titrations without indicators. And one is to use a pH meter. And so you can measure the pH, and then you graph the data, and from that graph you can determine the equivalence point. There are also other types of titrations, oxidation reduction titrations and other things, and a lot of those do involve some sort of a color change. But there are methods of measuring things besides that. It's just that that indicator is just very simple to use, doesn't require fancy equipment or anything. So here's an illustration. We have the sodium hydroxide in the burette. We've got acid in the flask. When we did this, we had the mass of the acid. And I told you, it doesn't really matter if your beaker's wet or not, and the exact amount of water that you stick in there doesn't matter, because we measured the mass. And so we can calculate the moles of acid. And that's really what we need, is we need to know the moles of acid in here. Then we add sodium hydroxide, and it reacts with the acid. And when we get to that equivalence point and the solution just starts to turn pink, then we measure how much sodium hydroxide we added. We can tell the number of moles of sodium hydroxide that were added based on the number of moles of acid that we knew were in the flask. And there it is with pictures instead of drawings. This is too pink. We don't really want to get that pink.
Maybe there's more indicator.
More indicator or more concentrated indicator will definitely affect that. And if you use more concentrated indicator, it can be really hard to get that pale pink.
So did you already know then? Did you make the concentration of the indicator so you knew what it was?
Well, the concentration of the indicator has some significance, but not a lot of significance. I told you to use 3 drops because I knew that it was a 0.1% solution. If you were using the 1%, then probably 1 drop would be enough. If you use a lot more indicator, all that's going to happen is that it's going to be, even a part of a drop might shoot you over into bright pink. You're still going to get the same result. Yeah.
What is dilute the molarity of the solution you're putting the indicator into?
Well, the question is, won't it dilute the molarity of the solution that you're titrating?
Right.
Because we measured the moles of acid that we put in there, the exact volume of that solution doesn't matter.
Oh, okay.
And so then adding more or less indicator doesn't matter.
Okay.
You can do
So
a
you
partial.
add a really dilute indicator if you wanted to.
Yeah, you could. The reason that you want it to be the same amount every time is you're going to get more accurate results if you go to the same color each time. And if you're using approximately the same volume of water and approximately the same amount of indicator, it's easier to realize that, okay, I'm getting a consistent color, I'm going to the same point in this reaction. If one of them is got 5 times as much water in it and the other one is more concentrated, then the colors aren't going to come out the same. Yeah.
So then also it helps then to measure out, like when we did on Tuesday, to measure out all your substance like the same weight?
Well,
Because wouldn't that throw off in like a concentration?
so the question is, should you have all of your masses be the same? You want them to be in the same ballpark because you want to use at least 10 milliliters of sodium hydroxide, but you don't want to need more than 25 because then you'll have to refill the burette and that's got some problems with it. You don't really want it to be exactly the same every time because what happens there, which is the same thing that happens when we start at 0 every time, is okay, that first one took 15.5 milliliters. Then you're expecting the second one to be 15.5. And there's going to be a subconscious bias to get that same number, when actually the first time you might have been off a little bit, and it shouldn't be exactly that. So that's why it's good to have slightly different masses for each. The exact concentration of that solution really doesn't matter. Those are good questions. Yes?
And there wouldn't be a trend at all? It would just be...
Well, the trend is if you add more acid, you're going to need to add more sodium hydroxide. But most people aren't going to do those calculations in their head or even do them ahead of time with a calculator to figure out, exactly how much should I be adding. You really want it to be more of a blind trial where you're just going by the color. I'm going to this same pale pink color each time, and then I'm going to do the calculations, and that'll get you better precision and accuracy than if you are trying to tweak it. Let's do an example of a calculation. So a titration of a 20 ml sample of an H2SO4 solution of unknown concentration requires 22.87 milliliters of a 0.158 molar KOH solution to reach the equivalence point. What is the concentration of the unknown H2SO4 solution? We need a balanced chemical equation. And the reason we do is that sometimes we're dealing, in this case we are, with a diprotic acid. Other times you might have a base that gives off more than one hydroxide ion. And so we need to use stoichiometry, and we need to not use the dilution equation. Do not use the dilution equation for titrations. It'll work sometimes, but it's a very bad habit, and it will not work all the time. So we need to look at the stoichiometry of this. Well, what are the products going to be?
H2 water.
Yeah, water and potassium sulfate. Now, if you're sitting there going, how did they do that? Let me show you. So this sulfuric acid has two ions in it, hydrogen ion and sulfate ion. Potassium hydroxide has two ions, potassium and hydroxide. We're going to swap the partners and write the formulas. So the H plus and the OH minus is what gives us the water. And we got the potassium sulfate from putting together K plus and SO4, 2 minus. Is the equation balanced? No, it isn't. We can really spot that when we look over here. K2SO4, there's 2 potassiums. So we need a 2 over here. And we've got 1 sulfate here and 1 sulfate there. That's okay. And then we've got these, let me circle them. We've got these hydrogens and these guys that we have not accounted for yet. So 2 hydrogens here and 2 more here. We need 4 hydrogens, so we need 2 water molecules. So I'm just going to get rid of this. It's in my way. So we have to have the balanced chemical equation. Now let's take those numbers and do stoichiometry. 20 milliliter sample of sulfuric acid, so 20.0 milliliters. We don't know what the concentration is. And then we know that we're using 22.87 milliliters of the potassium hydroxide. And we know that the concentration is 0.158 moles per liter. And our question is, how many moles per liter in the sulfuric acid solution? So this is a volume stoichiometry problem. Volume of one thing to moles to moles. What we need here to find out is we need the moles of sulfuric acid. They gave us the volume. So our path here is going to be milliliters of sodium hydroxide to moles of sodium hydroxide
Where
to,
did you get sodium?
I don't know. Thank you. Because it's always sodium. Potassium, thank you. Potassium hydroxide to moles of,
NaOH is in the beginning too.
thank you, I'll fix it. So again, we've got this milliliter-liter issue. There's different ways to deal with that. I'm just debating which one to do. No, I don't want to do that. Let's do this. Let's just take those volumes and convert them to liters. And then do the calculation. So I think by now many of you can convert from milliliters to liters kind of in your head. You're moving the decimal point 3 places. The danger is moving it the wrong way. So think about a 10 mil graduated cylinder and 1 milliliter in there. That's this little tiny amount, right? How big is a liter? It's half of a 2-liter soda bottle, right? So liter is the big unit, milliliter is the small unit. So if I go from a small unit to a larger unit, I need to take this larger number and make it smaller. Does that make sense? So this is going to be 0.02287 liters. If I did it the wrong way, I'd end up with 228,000 liters is equal to 22 milliliters. That's wrong. So stop and think about it, or bust out the dimensional analysis and do it that way. So there's our volume in liters. So I'm just going to go liters of KOH to moles. So I've got my liters, 0.02287 liters of KOH. And I'm going to go to moles of KOH. And then I'm going to go to moles of sulfuric acid. I'm going to stop there because I want the moles of sulfuric acid so that I can divide by the volume and get the concentration. What are they doing over there? It might be the plumber. There's a leaky sink in there.
Should the H2SO, should the KOH be 2 on the bottom for moles?
Yeah, so when we look here at the moles, this is where we need to use this balanced chemical equation. There's 2 moles of KOH for every mole of sulfuric acid. So 1 mole of sulfuric acid requires 2 moles of KOH. This other one, moles per liter, that's the concentration that we know. So 0.158 moles per liter. So we've got 0.00, no, just 10, 0.02287 times 0.158 divided by 2. So I've got 0.0018067. That would have 3 significant figures, but I'm going to keep 2 extras. Moles of H2SO4. To calculate the molarity, I'm going to take the moles and I'm going to divide by the volume in liters. 20 milliliters is how many liters? 0.02. 0.02, and then there's 2 zeros after that. Those are significant figures. So I'm going to take this number in my calculator and divide by 0.02. And then this should have how many sig figs? Should have 3 significant figures. 0.0, those don't count. 903, the next one is a 3, and so there's my molarity. This is similar to the calculation you did to find the sodium hydroxide, except with that one you had a mass of oxalic acid that you converted to moles, and then to moles of sodium hydroxide, and then you took the moles and divide by the volume in liters. Today in lab, you're going to be titrating citric acid. So you're going to have something a lot more similar to this. You're going to have a volume of acid and a volume of a known concentration of base. And so you're going to do a very similar calculation.
So our known concentration of the base will be what we calculated from experiment on Tuesday?
Yes. You standardize the sodium hydroxide on Tuesday, and so that is the concentration you're going to use to find the concentration of acid today.
Why do you divide by the liters?
Well, because molarity is moles of solute per liter of solution.
Gotcha.
And so this was the volume.
I was going on with the equation. And I was
Right.
trying to make- yeah.
And that's why I stop here and make this a separate calculation, because otherwise it does get confusing.
Gotcha.
Yeah.
So you said the molarity that we used from Tuesday, we're going to incorporate that into today?
Mm-hmm.
So if our number there is like really skewed, then it's going to throw this lab off.
Yep. Yeah. And really, standardizing sodium hydroxide on one day and then using it 2 days later is not ideal. Because as I mentioned, sodium hydroxide reacts with carbon dioxide from the air, and the hydroxide concentration goes down very, very slowly. But we're not using the results of this for anything, and we're all in the same boat, so it'll be okay. Any other questions? Gas evolution reactions. So here's an example of a gas evolution reaction. Potassium sulfide and sulfuric acid. So we're thinking of this also in terms of ion exchange or double replacement, where these ions are swapping places. What happens here is that we get potassium sulfate. So we had potassium and sulfide and hydrogen and sulfate. So the potassium and the sulfate are going to form potassium sulfate. And the hydrogen ions and the sulfide are going to form hydrogen sulfide. Hydrogen sulfide is a gas at room temperature. Now, why would you know that? You wouldn't know that. But I'm telling you now, so now you have to remember it. Hydrogen sulfide is a gas at room temperature. Most of the reactions we're going to see form a gas by decomposition of an intermediate product. If we look at sodium hydrogen carbonate, which is baking soda, reacting with hydrochloric acid. When we swap the partners here, we end up with sodium chloride and H2CO3. This is carbonic acid. Turns out carbonic acid is not stable. it decomposes into water and carbon dioxide. Now, we should all recognize that carbon dioxide is a gas. So what happens is it will fizz and bubble, and those little bubbles will come to the surface. This is a similar reaction to when you mix vinegar and baking soda. It bubbles because it's forming carbonic acid, which is unstable and decomposes into water and carbon dioxide. Here's illustrations of this. Here we've got our sodium hydrogen carbonate, and here we've got our hydrochloric acid. And they form an intermediate product of carbonic acid, which then falls apart and forms CO2. And we see this as bubbles that float to the surface. So, you need to know 4 different types of gas evolution reactions. The first one does not have an intermediate. This is when you have a sulfide, and when one of your products is H2S, you just have to remember that's going to be a gas. Dihydrogen sulfide gas smells like rotten eggs. It's very, very stinky gas. The other 3 types do involve an intermediate. If you get carbonic acid or sulfurous acid or ammonium hydroxide forming, those are going to decompose. And there is a pattern among these 3 that makes it a little bit easier to remember. So basically you need to memorize those 3 compounds, and then I'll show you how you can figure out what they decompose into. So H2CO3, and we've got H2SO3, and we've got NH4OH. What these are going to do is they're going to separate into a water molecule and then whatever's left. So if I take H2O out, so there's the 2 H's. Let me switch to a different color here. So we're going to take out the 2 H's, and there were 3 oxygens. We're going to take out one of them to be in the water. And what's left? CO2. CO2 is a gas. And then let's look at H2SO3. Well, that's going to decompose into water, and what's left? Well, let's take the water out. There's the H2 gone. We lose one of the oxygens, and we get SO2. Sulfur dioxide, also a stinky gas.
So when the intermediate products are produced, we can automatically just switch that over to
Yes.
what it should be.
So you do the ion exchange, you swap the partners. If one of these is the product, then you need to know to take that and decompose it into this, and these are the actual products, not the carbonic acid.
So we have to decompose it.
You
We
have
can't
to
just make
decompose
a
it.
gas.
Yeah. And then with ammonium hydroxide, this is going to do the same thing. It's going to lose a water molecule, and then we're going to look at what's left. Well, we need to lose 2 hydrogens, so I'll take them both out of here. So then I've got 2 hydrogens left there, and I'm going to lose that 1 oxygen. I'm pulling the H2O out. What's left? 3 H's and an N. That's ammonia. Ammonia is a gas. Also smells nasty. It'll burn the inside of your nose really well. So these are examples of those reactions. Ammonium chloride and potassium hydroxide. When you swap the partners here, you get KCl and ammonium hydroxide. And then we remember, oh, ammonium hydroxide does this. It makes water and ammonia. And so those are the products here. Any questions? Yes.
What's the H2S like? I know it's what comes out, but there's nothing that leads to it.
No, this one doesn't have an intermediate. And so it'll be a reaction like this where you just swap the partners and you get the H2S. And you just have to remember that's a gas. Let's do an example. Write a molecular equation for the gas evolution reaction that occurs when you mix aqueous hydrobromic acid and aqueous potassium sulfite. Well, aqueous hydrobromic acid, what's the formula for hydrobromic acid? HBr. The hydro prefix tells us this has no oxygen in it. It's just hydrogen and bromine. That's aqueous. The ions here are H plus and Br minus. And then potassium sulfite. Well, that's K plus. It's not a very good K. And what's the formula for sulfite? SO3, 2 minus. So, because we need to look at the charges so that we can know how to write the formula. It's K2SO3. And that's aqueous. We're going to predict the products by just swapping ions and seeing what we end up with. So we're going to get K plus and Br minus, and we're going to get H plus and SO3, 2 minus. So that gives us KBr. Is that soluble? Yeah, potassium compound's always soluble. And H2SO3. Then your brain should go ding, ding, ding. That's one of those gas ones. It's kind of a clue here, the gas evolution reaction. That decomposes. So this decomposes into water, and what's left after we remove the water from H2SO3? SO2, and that's a gas. So this is all very messy, so let's rewrite this and then make sure it's balanced. So we had HBr, aqueous, plus K2SO3, aqueous, forms KBr, aqueous, plus H2O, liquid, plus SO2, gas. I'm not going to write the intermediate, I'm going to write what it decomposes into. Then we need to balance it. So I'm looking at potassium. Potassium's not balanced. So I'm going to put a 2 here. So we've got 2 potassiums and 2 potassiums. And then I'm going to check out the bromine. There's 2 bromines. So then I need to go over here and put 2 HBRs. Now I've got 2 hydrogens on the left and 2 hydrogens on the right. Here I've got 1 sulfur and 1 sulfur, 3 oxygens, and 1 plus 2 is 3 oxygens. This is a situation where that polyatomic ion did come apart. We don't have sulfite anymore. Any questions?